Good afternoon, class. In today's video, what I wanted to do was to talk about nuclear fission. So in this one, last time we went over nuclear fusion where it was small atoms coming together, fusing, and becoming a bigger atom. This time we're taking a bigger atom and we're going to split it up into smaller atoms. So here we go. The typical nuclear fusion reaction is U-235 plus one neutron. It breaks down into krypton 92 plus barium 141 plus three more neutrons plus some energy. And of course, there's the conceptual side and then there is the mathematical side. And today I wanted to focus on the mathematical side because we can actually focus now on the comparison between the two. Because if we're going to use a type of nuclear power for our energy needs, we should probably pick the best one. And of course, it would also behoove us to understand why we picked nuclear fission first. So once we get that idea, once we understand how much energy is produced, hopefully that will motivate us to make better choices as a species in terms of the health of our planet. So let us begin. So once we've done all that, what I did was I did a little bit of research. I looked up several of the atomic mass units for which I detailed what they were in the last video. But I found out the atomic mass of uranium-235 plus a neutron, and the atomic masses for krypton and barium plus the other three neutrons. And I figure I'll just let you read them as they are up there on the board. Notice I did round a few of these numbers, mostly because I was running out of space and I didn't want to smash everything so close together. So just know that these numbers here are rounded a little bit. So how much energy is released? Because we've got this, we see this 236.0529299 AMU. We've got this one as 235.827 AMU. Wonderful, right? We've got that the mass is almost equivalent, but not quite. There's a little bit of a mass difference, and that mass difference is going to get converted into energy. Of course, really, the question is, how much energy is that? So there we go. Let's do some math. How much energy is released? Because that's going to be 3.75 times 10 to the negative 28 kilograms. This is per reaction. So that's how much mass is being converted into energy at this point. So we're using E equals mc squared. We're going to find that our answer is going to be about 3.375 times 10 to the negative 11th joules per reaction. But to make things equal and fair, right? Because in the last one we had two hydrogen or two deuterium atoms smashing into each other, combining. So if you had a kilogram of deuterium, then you would only have half of them be able to react and give you helium. But in this case, all you need is every uranium atom is going to be reacted. In this case, is going to have a reaction. So what we would need to know is how many. So we know how many joules are released per reaction, but really how many reactions are taking place? And if I took the same amount, 1 kilogram of that substance, how much energy would I get out of it? So let's find out. In 1 kilogram of U-235, there are 2.56 times 10 to the 24th reactions, which means that there are 2.56 times 10 to the 24th atoms, because each one of the atoms can react and spontaneously split. So that's why I counted them as basically I doubled the number of reactions that could take place in a kilogram of uranium. So when we take a look at that, the energy for that comes out to about 1.8 times 10 to the 13th joules. Now, again, this is not the most precise number that I could find because I did do a little bit of rounding. So, I don't want you to think, oh, he got a nice answer there. It's rounded. So, the conclusion that I have is going to have a little bit of, when I compare the two, the numbers that I'm going to throw out there are, won't be necessarily what you might find on a Google search of how much energy, what's the comparison between these two reactions, mostly because I did some because of this rounding error. So I just wanted to make sure I pointed that out. But let's compare, right? We've got fusion now. I've got 1 kilogram of deuterium, and there are 1.56 times 10 to the 26 reactions because deuterium is just a much smaller atom, so you can fit more into that 1 kilogram. And also they're very light. So when you've got heavy atoms versus light atoms, the energy for that is going to come out to about 2.18 times 10 to the 14th joules. So we might some people who are not versed in the scientific notation would look at this and go, okay, 1.8 times 10 to the 13th, 2.18 times 10 to the 14th, doesn't seem to be too much of a difference. But actually, in terms of energy output, this is 10 times, I mean, it's not exactly 10 times, it's almost 10 times more than this. So this reaction will get you, 1 kilogram of this will give you this much energy, but you get about 10 times more if you had a kilogram of deuterium. And now here's the question. Then we have other things that need to come up in the discussion of which one are we going to choose, nuclear fission or nuclear fusion. And some things you have to consider are, how easy is it to get access to uranium? It's not actually all that easy. You have to find it somewhere. It's somewhere buried underground. You have to find it, and then you have to mine it and pull it out of the ground. Then you have to use all of the uranium, if you can, which a lot of times when we have these things called spent fuel rods, they've only reacted with like 5% of the fissionable or the fissile material. So, in terms of economics, it's not really a great investment to try and make uranium-235 if you're going to just use it for power, because all you can only use about maybe 5-10% of it before it's just worthless, and you have to just throw it out and and put it into the ground, put it back into the ground. But this time it's a whole lot more radioactive, because when you pulled it out as uranium, it was naturally in the ground. So if you put all that stuff back in the ground, then that would be fine, because it would be doing the natural process that that was going through it. But we mined it, and let's say we pulled it out of, let's say, somewhere in the United States. Well, we ship it to all other parts of the country. We might even ship some of that uranium to Canada. And so if Canada has it and they use it, they can't put it back in their ground. The environment over there does not help, or does not allow for that kind of radiation to be present and have everything survive. Whereas if you found a uranium mine, the environment around that uranium mine has already adapted to that level of radiation. So you would be causing pretty extreme, some pretty extreme effects on the environment if you just buried the uranium right where you use the reactor for it. So that's why people have to really seal the uranium in, and they have to just put it in very tight drums and seal them really well, and just basically leave them there for thousands, and we're going to leave them there now for thousands of years until they finish reacting and they're determined safe. So that is unfortunately one of the products of a nuclear fission reaction. Okay, like I said in the last video, the product of a nuclear fusion reaction is helium and some heat. Versus in the nuclear fission reaction, not only do you have krypton, barium, plus three extra neutrons, and you've got the heat already, which is what we wanted, but you've got now radioactive krypton, radioactive barium, and 3 other neutrons that are just flying all over the place. That can be bad. That can lead to severe health effects, because each of these are going to break down now. So you've got more radiation that's going to keep going down the line, and that could be also very bad for all of the people, and the environment around it. However, is it easy to build a nuclear power plant, a nuclear fission power plant? Because once you get all of the uranium, the answer is actually quite easy. What you do is you just take the design, the basic setup of a coal-fired power plant, and you use that uranium, and then you just replace the fuel with a nuclear core of uranium, a uranium-filled core, and now you can make lots of energy. I mean, still a lot of energy, but you'll make a lot of it, and it's very cheap to build. However, the cleanup is the real problem. That's where all of the bad effects come from. Whereas with fusion, the upfront costs are really, really high in terms of the technology and how to actually build it, where you can build it, because it's not like I can ship seawater to any place I want on Earth. I have to actually have a source to build, so that it limits how many power plants I can actually build of nuclear fusion power plants. But with nuclear fission power plants, I can build them anywhere. They're very cheap to build. The setup has already been kind of fairly perfected using our coal-fired power plants before. So the only thing left is just the cleanup, which that has massive costs. So that's all. I just wanted to use this video to present the facts about that. You know, how we deal with it in terms of our policies, and how we deal with it as a culture, as a country, and as a species. That's another video that would be a whole separate matter. I just wanted to present some of the facts about what it would take to have nuclear power, the types of nuclear power in fission and fusion, and which ones would be worth pursuing, especially when it's very easy to get all of these fusion, all the materials for a fusion power plant, and not so easy to get it for a fission power plant. So that concludes this video. Good luck in your studies, and may the force be with you.